Introduction to the cloud. As the popular saying goes, the cloud is just somebody else's computer. There is no magic. Just using the cloud does not magically solve the problems we are having with a traditional infrastructure. This lecture will teach you how a cloud is built and what the typical services are that they offer, as well as the pitfalls which may come with such setups. What is a server? In older times, servers were completely different from the machines we used for regular work, not just in weight and form factor, but in architecture. The landscape would stretch from SPARC and Power architectures to the x86 architecture we use in our PCs. Over time, however, the x86 architecture took over to the point where a server today, from an architectural standpoint, is exactly the same as the machine you are using right now. This means that you can copy the machine you are using onto a server, and chances are it will run without any modification. The only notable exception is the rise of the ARM architecture, which is popular in phones and tablets and is known for its low power consumption. In recent years, there has been a small but noticeable trend to run ARM in a data center. At home, it might not matter if your computer uses 200 or 300 watts of power. In a data center, at the scale of hundreds or thousands or tens of thousands of servers, saving even a few % of power will translate to huge cost savings. The difference in build is, however, quite apparent. While some servers, mainly built for office use, have the standard tower build, most servers have a flat profile designed to be mounted in racks. Since most servers are not high enough to take a full-size expansion card such as a graphics card or network cards, servers may contain a separate removable component for these, usually called a riser. Server racks are standardized closets that have mounting screws for rails that allow pulling out servers even mid-operation and replace components while the server is running. Servers also come with a high level of redundancy. While you may have a single power supply in your home computer, servers typically have two that are able to take power from different power inputs. This makes sure that servers keep running even if one of the two power supplies fail, or if one of the two power inputs goes down. Also, in contrast to your home setup, these servers contain an out-of-bounds management interface that allows remote management of servers even when they are turned off. The hardware components built into the server report their health status to this OOB management interface, which allows for the simultaneous monitoring of thousands of machines. Please note, this is a fairly generic description of servers. Different vendors may choose to leave out certain features of their more budget line of servers or call different components differently. HP, for example, calls their out-of-bound management interface Integrated Lights Out or ILO, Dell DRAC, as in Dell Remote Access Control, etc. When it comes to purchasing servers, larger companies tend to go with the same components for a longer period of time, and they also buy support from the vendor. This sometimes includes hardware replacement done entirely by the vendor in the data center without the need of the customer staff being on site. However, purchasing a specific set of components or ordering larger quantities of servers presents a logistical challenge and can sometimes take up to 3 to 4 months. Buying hardware is also an upfront investment, which is hard to justify when demands change rapidly. The anatomy of a data center. Since the cloud is just somebody else's computer, that computer needs to be hosted somewhere. Servers are almost exclusively hosted in data centers. Let's take a look at what is involved in running a data center. First of all, as mentioned above, most servers are going to be rack-mounted, so you need a bunch of racks. These racks are installed in rows, often with a fake floor to allow for cabling to go under the floor. Since servers produce a lot of heat, a data center also requires cooling. There are a variety of ways to solve cooling, some are more green than others. Some data centers, for example, opt to install cold aisles, where the cold air is pumped between two rack rows and is pushed through the racks to cool the servers. Apart from cooling, data centers also require automated fire suppression systems simply because of the amount of electricity going through. Data centers usually go with a non-destructive fire suppression system, such as lowering the oxygen content of the air enough to stop the fire. All critical systems in a data center, such as power, cooling, or fire suppression systems, are usually built in a redundant fashion because the loss of either of those systems will potentially mean a complete shutdown for the data center. Data center operators usually have further contingency plans in place too. such as a UPS, as in a battery, a diesel generator, and a fuel truck on standby for that diesel generator, a hotline to the fire department, etc., to make sure that the data center can keep its required uptime. On the networking side of things, matters get slightly more complicated. Some data centers also offer you the ability to use their network uplink. Also redundant, of course, but larger customers will prefer to host their own networking equipment and negotiate their own internet uplink contracts. Since there is no generic rule for how data centers handle this, we will dispense with a description. It is also worth noting that larger customers such as banks, cloud providers, etc. usually prefer to have their own racks within a separated gated area called a cage, to which they control access. The anatomy of the internet. Once the physical infrastructure is set up, there is also the question of how to connect the internet. As mentioned before, networks can be complicated and there is no one-size-fits-all solution. Smaller customers will typically use the network of the infrastructure provided by the data center, while larger customers will host their own networking equipment. Again, generally speaking, racks will be equipped with a top-of-rack switch to provide layer 2 or Ethernet connectivity between servers. Several top-of-rack switches may have interconnects between each other and are usually connected to one or more routers. Routers provide layer 3 or IP routing to other customers in the same data center or internet exchange, or may be connected via a dedicated fiber to another provider. Note: if you're not familiar with computer networks, we recommend giving the Geek University CCNA course a quick read. While you will not need everything, you will have to understand how IP addresses, netmasks, etc. work in order to pass this course. Providers on the internet exchange data about which network they are hosting using the Border Gateway Protocol, or BGP. Each provider router announces the IP address ranges they are hosting to their network peers, who in turn forward these announcements in an aggregated form to other providers. Providers have arrangements with each other or an internet exchange about exchanging a certain amount of traffic. These arrangements may be paid if the traffic is very asymmetric or one provider is larger than another. Alternatively, providers can come to an arrangement to exchange traffic for free. Internet exchanges facilitate the exchange between many providers for a modest fee, allowing cost-effective exchange of data. Depending on the exchange, the local rules are different. Local exchanges, for example, may only allow advertising local, in-country addresses, while others are built for a very specific purpose. Generally speaking, providers can be classified into 3 categories. Tier 1 providers are the global players that are present on every continent. They form the backbone of the internet. At the time of writing, there are 16 such networks. Tier 2 are the providers who are directly connected to the Tier 1 providers, while Tier 3 is everyone else. Software stack. The purpose of all of this is, of course, to run an application. Each server hosts an operating system which is responsible for managing the hardware. Operating systems provide a simplified API for applications to do hardware-related operations, such as dealing with files or talking to the network. This part of the operating system is called the kernel. Other parts form the userland. The userland includes user applications such as a logging software. Specifically on Linux and Unix systems, the userland also contains a package manager used to install other software. Modern x86 server CPUs and also some desktop CPUs also have a number of features that help with virtualization. Virtualization lets the server administrator run multiple guest operating systems efficiently and share the server resources between them. Did you know? You can find out if an Intel CPU supports hardware virtualization by looking for the VT-X feature on the Intel ARC. Unfortunately, AMD does not have an easy-to-use list, but you can also look for the AMD-V feature on AMD CPUs. Note: virtualization is different from containerization, which we will talk about later, in that with virtualization, each guest operating system has its own kernel, whereas containers share a kernel between them. There is one more important aspect of finally getting an application to run: the runtime environment. Except for a few rare occasions, applications need a runtime environment. If the application is compiled to machine code, they still need so-called shared libraries. Shared libraries are common across multiple applications and can be installed and updated independently from the application itself. This makes for a more efficient update process, but also means that the right set of libraries need to be installed for applications. If the applications are written in higher level languages such as Java, JavaScript, PHP, etc., they need an appropriate runtime environment for that language. One notable exception to the runtime environment requirement is the programming language Go. Go compiles everything normally located in libraries into a single binary along with the application. This makes it exceptionally simple to deploy Go applications into containers. The cloud. All of the previously discussed things were available before the cloud. You could pay a provider to give you access to a virtual machine where you could run your applications. What changed with the cloud, however, is the fact that you no longer have to write a support ticket, and everything became self-service. The cloud age started with an infamous email from Jeff Bezos to his engineers in 2002, forcing them to use APIs to exchange data between the teams. The exact email is no longer available, but it went along these lines. 1. All teams will henceforth expose their data and functionality through service interfaces. 2. Teams must communicate with each other through these interfaces. 3. There will be no other form of inter-process communication allowed. No direct linking, no direct reads from another team's data store, no shared memory model, no backdoors whatsoever. The only communication allowed is via service interface calls over the network. 4. It does not matter what technology is used. HTTP, CORBA, PubSub, custom protocols does not matter. 5. All service interfaces, without exception, must be designed from the ground up to be externalizable. This is to say, the team must plan and design to be able to expose the interface to developers in the outside world. No exceptions. 6. Anyone who does not do this will be fired. This marked the beginning of Amazon Web Services, the first and also most successful public cloud offering. The first public release of AWS was in 2004 with SQS, their message queue service, and got completely overhauled in 2006 where the Elastic Compute or EC2 and the Simple Storage Service or S3 service made its first public appearance. The APIs provided by the cloud providers allow for a large amount of flexibility. If new servers are needed, they can be launched within a few minutes. If there are too many servers, they can be deleted. The same goes for other services. With the API and the appropriate billing model comes flexibility to adapt to change. The other factor that makes it easy to adapt to change is of course the fact that these services are managed. The cloud customer doesn't need to hire a team of engineers to build a database service, for example. It can be consumed without knowing how exactly the database is set up. If you want a concise description of what cloud computing is, the US National Institute for Standards and Technology, or NIST, has described cloud computing in their publication 800-145 as follows. Cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, example network, servers, storage applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. In more detail, NIST has defined the following characteristics. 1. On-demand self-service. 2. Broad network access. 3. Resource pooling. 4. Rapid elasticity. And 5. Measured service. Generally speaking, cloud services can be classified into 3 categories. Infrastructure as a service, or IaaS, providing virtual machines and network infrastructure. Platform as a service, PaaS, offering services for developers to use, and Software as a Service, or SaaS, offering end-user services. This is described in the above NIST publication. Infrastructure as a Service. The most basic of cloud offerings is IaaS. Infrastructure as a Service means that the cloud provider will manage the infrastructure used by the customer. Infrastructure in this sense means the ability to manage, provision, start-stop virtual machines. In very rare cases, some providers also offer bare metal machines in this fashion. However, most bare metal providers do not offer a true IaaS, as machines cannot be ordered using an API, have an upfront fee, and are billed on a monthly basis. Infrastructure as a service also includes the network connectivity to the internet. Almost all IaaS providers also offer a built-in firewall, virtual private networks, VPCs, that can be used to connect virtual machines together without sending traffic over the internet, and other network services. Note that the network services can differ greatly. For example, some providers implement private networks on a regional basis, while other providers offer private networks that can be used to connect virtual machines that are located in different regions. Managed services or platform as a service. Apart from offering virtual machines and network infrastructure as a service, many cloud providers also offer additional services that are typically used by developers, such as managed databases. These services are managed in the sense that the developer does not need to run the operating system and the database software itself. However, the developer has to configure the database such that it works according to the needs of the application. The provider takes over the duties like installing the service, making backups, monitoring, and restoring the service in case of an outage. Did you know? There are purely PaaS providers that do not offer IaaS, only a developer-friendly platform to run the software on. Your run-of-the-mill PHP web hosting provider does qualify if you can order the service using an API. One notable exception that rose to prominence is Heroku. The pricing of these managed services varies greatly, but they usually follow the cloud model. Most cloud providers offer at least a low-cost or even free entry version that has a small markup on top of the IaaS costs. The massive benefit of using these managed services is, of course, that you do not need to have an in-house knowledge about how to operate them. You don't need an in-house database operator, you just need to know how to set up the database in the cloud. This lets your company focus on the core business that they're trying to build and outsource the know-how required to build these services on top of the IaaS layer. As you might imagine, managed services also have downsides. Most importantly, they present a clear vendor lock-in. This means that if you want to move to a different cloud provider, you will have a hard time doing so if you are using one of the more specialized services. In other words, the level of standardization across providers matters. It is also worth mentioning that managed services tend to work well for a large number of customers, but a few number of customers can run into hard-to-debug problems. This debugging difficulty arises out of the inherent opacity of the service. You, the customer, don't see what's happening on the IaaS layer. If a database, for example, fills the available bandwidth, you might not be notified and left guessing why your database misbehaves. Business models. The flexibility of cloud providers comes from their usage-based pricing. This can vary depending on the type of service used. For example, virtual machines or IaaS is typically priced on a per-second basis. When you start a virtual machine for only 5 minutes, you only pay for 5 minutes of runtime. This lets you optimize the cloud usage cost if you use automation to start and stop machines or services on demand. Typically, the cost savings are realized in these scenarios. On-off usage. This usage is typical for batch processing. Machines are only started when there is a workload, for example, video conversion, machine learning training job, etc. Growth usage. Projects that see a growth curve often opt to use a cloud provider as well, since buying hardware in larger quantities typically takes 2 to 4 months. Sudden spike usage. Cloud providers can also be useful if a service encounters a sudden load spike. This is typically the case for web shops around Black Friday or other sales events. Periodic spike usage. Almost every service has usage spikes depending on the time of day. This can be used to scale the service up and down. Per request billing. IaaS services are typically priced based on an allocated amount of resources determined at the start of the virtual machine. Some PaaS services also use this billing model, typically databases as a service. Other PaaS services often opt for a per request or data volume-based billing approach. Cost planning with the cloud. Cost planning is an important part of the job of a cloud architect. Depending on the billing model of the cloud provider, this can be fairly simple to almost impossible. As a rule of thumb, the billing model of larger cloud providers such as AWS, Azure, or Google Cloud is more complex than smaller cloud providers such as DigitalOcean, Exascale, UpCloud, etc. It is worth noting that the data transfer is typically charged based on volume. Some cloud providers even charge for internal traffic between availability zones. Cost comparison with on-premises systems. One of the most important cases for cost analysis will be the comparison with an on-premises architecture. It is quite common to create a cost comparison where the investment required for a hardware purchase is compared with the cloud cost over 3 or 5 years. These comparisons can be quite misleading because they often don't contain any cost attribution for the required work, and they also do not use the advantages of the cloud in terms of scaling. Without these factors, a hardware purchase will almost always be cheaper when calculated over 5 years and be roughly equal when compared over 3 years. Private versus public cloud. Most cloud applications will reside on a public cloud and be accessible from the internet. However, for some use cases, access over the public internet is not desirable or even strictly forbidden by laws or regulations. In other cases, companies may decide that it is their policy that certain systems must never be connected to the public internet or connect only via a self-hosted gateway. In these cases, a private cloud is desirable to minimize the risk of cross-contamination or data exposure due to the other tenants being on the same infrastructure. Such cross-contamination is not uncommon. For example, in recent years, there have been a litany of CPU bugs such as Meltdown and Spectre. A special form of a private cloud is a cloud offering that is dedicated to a special set of customers, such as a research cloud with special hardware or discounted rates for several research organizations or universities. The NIST classifies this as a community cloud. Public cloud providers have extended their offers to address these concerns. Their service offerings now include dedicated hypervisors to mitigate CPU bugs, the ability to connect the cloud using a non-internet connection such as an MPLS tunnel, or accessing the cloud's API from a private network. Some cloud providers even went as far as offering a self-hosted setup, where the public cloud offering can be brought on-premises. These features, especially the connectivity-related features, also allow for the creation of a hybrid cloud, where the traditional infrastructure can be connected to the cloud. This gives a company the ability to leverage the flexibility of the cloud, but also keep static or legacy systems for financial or engineering reasons. While the definitions outlined by NIST and other organizations in this matter are clear, real life rarely is. In a real-world scenario, you will find a wide range of mixes comprised of all of the above. To you as a cloud engineer, it is most important to understand the benefits and the drawbacks for each, so you can make a good recommendation depending on the use case. Automation. As you can see from the previous sections, cloud computing doesn't necessarily make it simpler to deploy an application. In this regard, setting up a bare metal server and not documenting it is the same as setting up a cloud and not documenting it. In the end, in both cases, modifications will be hard to carry out, since the details of the implementation are lost. It will also be hard to create a near identical copy of an environment for development, testing, etc. purposes. This is partially due to the lack of documentation and also partially because the manual work involved. In the past, this problem was addressed by cloning virtual machines, which was an approach with limited success as customizations were hard to make. The rise of APIs brought a much welcome change. Automation tools such as Puppet, Ansible, and Terraform not only automate the installation of certain software, but also document how the setup works. When engineers first go onto automation, they tend to reserve a part of the work to be done manually. For example, they might use Ansible to create a virtual machine and then install some basic tools and install the rest of the software stack by hand. This approach is workable where the software stack cannot be automated, but should be avoided for software where this is not the case, as the lack of automation usually also means a lack of documentation, as described above. Automation tools are also not equally suited for the task. Terraform, for example, expects full control of the infrastructure that it created. Manual installation steps afterwards are not supported. This approach gives Terraform the advantage that it can also remove the infrastructure it creates. Removing the infrastructure is paramount when there are multiple temporary environments deployed, such as the development or testing environment. Ansible, on the other hand, allows for manual changes but does not automatically implement a teardown procedure for the environment that it has created. This makes Ansible environments and Ansible code harder to test and maintain, but is more suited for environments where the traditional IT is still a concern. Regulation. General Data Protection Regulation, or GDPR, in the EU. The GDPR, or DSGVO for German-speaking countries, is the general overhaul of privacy protections in the EU. The GDPR replaces much of the previously country-specific privacy protections present in the EU. Jurisdiction. The GDPR applies to all companies that deal with the data of EU citizens around the globe. This is made possible by trade agreements previously already in place. All companies that handle the data of EU citizens, even if the companies are not located in the EU. Structure. The data subject is the person whose data is being handled. Personally identifiable information, or PII, is the data that makes it possible to uniquely identify a data subject. PII can also be created when previously non-PII data is combined to build a profile. The data controller is the company that has a relationship with the data subject and is given the data for a certain task. And the data processor is a company that processes data on behalf of the data controller. The data processor must have a data processing agreement, or DPA, with the data controller. IaaS and PaaS cloud providers are data processors. Purposes of data processing. One new limitation of the GDPR brings to privacy regulation is the fact that there are fundamental limits to data processing. You, the data controller, cannot simply collect the data for one purpose and then use the same data for another purpose. The purposes to which the data is collected have to be clearly defined, and in several cases the data subject has to provide their explicit consent. In other words, it is not enough to add the text to the sign-up form that says that they agree to everything all at once. Legal grounds for data processing are detailed in Article 6 of the GDPR. These are: 1. If the subject has given their explicit consent to process their data for a specific purpose. 2. If the processing is necessary to perform a contract with the data subject. In other words, you do not need additional consent when you are processing data in order to fulfill a service to the data subject. 3. To perform a legal obligation. For example, you have to keep an archive of your invoices to show in case of a tax audit. 4. To protect the vital interests of the data subject or another natural person. 5. To perform a task which is in the public interest, or if an official authority has been vested in the data controller. 6. For the purposes of a legitimate interest of the data controller, with exceptions of course. This might seem like a catch-all, but courts have defined legitimate interest very narrowly. The data controller must show that the legitimate interest exists and cannot be achieved in any other way than with the data processing in question. One good example for the legitimate interest clause would be a webshop that is collecting the data about their visitors in order to spot fraudulent orders. Data subject's rights. Chapter 3 of the GDPR deals with the rights of the data subject. These are: 1. The right to be informed. This right lets the data subject request several pieces of information: the purposes of processing, the categories of personal data concerned, who received their data, in particular recipients in third countries or international organizations, how long the data will be stored, the right to request modification, deletion, or restriction of the processing, the right to log a complaint, the source of the personal data, if not provided by the data subject themselves, and if and how automated decision-making profiling is taking place. 2. The right to fix incorrect data. 3. The right of deletion, or the right to be forgotten. This right puts several architectural limits on the cloud system as, for example, backups must be built in such a way that deletion requests are repeated after a restore. Note that this right is not without limits. Legal obligations, for example, override it. 4. The right to restrict processing. If a deletion cannot be requested, the data subject can request that their data should only be processed for the purposes that are strictly required. 5. The right to data portability. The data subject has to be provided a copy of their data in machine-readable form. 6. The right to object automated individual decision-making and profiling. Data breaches. Chapter 4, Section 2 is probably the first legislation around the world that explicitly requires security of data processing from companies that handle personal data. Article 33 of this chapter specifically requires that data breaches must be disclosed to the supervisory authorities. Supervisory authorities in turn have the right to impose fines up to 4% or 20 million euros of the global revenue of a company. This means that companies can no longer sweep data breaches under the rug and must spend resources to secure their data processing. In the scope of the cloud, this means that our cloud environment has to be set up in a secure way to avoid data breaches. The Cloud Act, 2018, USA. The Cloud Act, or House Rule 4943, is the latest addition to the US legislation pertaining to cloud providers. This act says that a cloud provider must hand over data to US authorities if requested, even if the data is stored in a different country. This act has been widely criticized and is, according to several legal scholars, in contradiction with the GDPR. The large US cloud providers have opened their subsidiaries in the EU in order to try and shield their European customers from this act, and a few purely European cloud providers have also capitalized on this. It remains to be seen how effective this move is. The Digital Millennium Copyright Act, or DMCA, 1998, USA. The DMCA clarifies how copyright works in the USA. Since the USA is part of the WIPO Treaty and a significant amount of providers are based in the USA nowadays, all countries align themselves with the DMCA when it comes to dealing with online copyright infringement. Title II of the DMCA creates a safe harbor for online service providers against copyright infringement committed by their users. However, they have to remove infringing content as soon as they are properly notified about it via an DMCA takedown notice. The author of a DMCA takedown must swear by the penalty of perjury that they are, or are acting on behalf of, the copyright owner. If they were to make this pledge in bad faith, they could end up in prison. If the DMCA takedown notice has been sent erroneously, the original uploader is free to send a counter notification, also swearing under the penalty of perjury. In this case, the provider notifies the original sender and restores the content. The original sender then has to take the uploader to court and pursue the matter further. Communications Decency Act Section 230, 1996, USA. This section of the CDA is very short. No provider or user of an interactive computer service shall be treated as the publisher or speaker of any information provided by another information content provider. To someone not well versed in US legal lingo, this may sound like gibberish, but it is, in fact, one of the most important pieces of legislation pertaining to operating platforms in the cloud. In US legal history, the speaker or publisher of certain information is responsible for the information being provided. Before the CDA, any provider hosting illegal content would be responsible for said content. The CDA changed that by shielding providers from liability. This included web hosting providers as well as newspapers that had a user content section. The CDA is not limitless. Providers still have to remove infringing content if notified. They may also employ moderation proactively. Fall of Privacy Shield and Standard Contract Clauses, 2020, EU-US. The Privacy Shield Agreement in 2016 was the successor of the failed International Safe Harbor Privacy Principles Framework and was intended to protect the privacy of EU citizens when using US services or their data is transferred to the USA. The Privacy Shield has been enhanced in 2017 with the EU-US Umbrella Agreement, which fixed many of the issues with the Privacy Shield. Unfortunately for cloud users, Privacy Shield has been invalidated by the European Court of Justice. This decision means that you, as a European cloud user, can no longer automatically use a US-governed cloud provider without accepting liability. Instead, US data processors have to use one of the 3 standard contract clauses approved by the EU. The first standard contract clause states that both parties, you as the cloud user and the cloud provider, are both jointly and severally liable for any data breaches. The second is more business-friendly and merely makes sure that both the European party and the non-European party uphold their obligation to handle data with due care and implement protection measures. Shared liability would only apply if the terms of the SCC were breached. While this is a step forward, it is worth noting that this puts the responsibility on the cloud customer if the cloud provider breaches the terms by, for example, handing over data to the US authorities covertly. The third standard contract clause is the one that was adopted by Google and AWS, for example. It creates a safety net for the cloud provider by only requiring them to disclose requests by law enforcement if that would not put criminal liability on them. It also puts any liability for damages on the cloud user unless they, for example, went bankrupt. In that case, the cloud provider is only responsible for their own operations, not those of the cloud user. In other words, you, the cloud user, are responsible for any breaches of data to US law enforcement requests.